Hey guys, welcome back to the paper reading time. So today I'm going to read this sort of comprehensive paper on quantum computing and sort of analyze what it's got to offer. Now the challenge is that I don't have that much time. I only have 26 minutes because I've got a Bible study at 9 p.m. tonight. So I'm going to read as much as I can and maybe pick up tomorrow. All right. Does the abstract say? Abstract quantum computing is better than traditional CMOS. It's like traditional semiconductors. Its potential to revolutionize today's computing. Okay, so due to the involvement of quantum properties, many beginners find it difficult to follow the field. Okay, so an effort has been made to introduce various topics to people with not as strong of a background. Historical background, basic concepts, introduce it in a lucid manner. Okay, so it's supposed to be beginner friendly, and obviously I'm an extreme beginner, so I'm a I'm a learner, right? Gotta pick up. Okay, DiVincenzo criteria, so like NISQ related stuff, ion trap space quantum computing, superconducting quantum computing, NMR quantum computing, spintronics and semiconductor based quantum computing. Okay, so a lot of architectures at the end, and then some basic implementations, I guess. Okay, okay, this sort of gives an introduction. Why is quantum computing good? Okay, it's important to accomplish computing deals with problems. Yeah, attracting a lot of money and big tech, especially Google and Intel and IBM, but Intel's sort of dying, so mostly Google and IBM. Accepted in the 1980s. First computer, D-Wave. So D-Wave has been around for some time. 128 qubits in 2010. Wait. Wait. Where are you getting these 2,000 qubits? Huh? Whoops. Yeah. Where are you getting these 2,000 qubits? I thought the state of the art only has like slightly over 100. Maybe this is referring to not error corrected qubits. But yeah, the publications have obviously gone up. This will probably be a lot higher. Computers aren't constrained to two states. Yeah, so this is like qubits using entanglement. Similarity of silicon qubits with CMOS. Foundries is an extraordinary resource. Yeah, so the advantages compared to classical computers are that number one, it scales faster. Number two, it transmits info quickly. And number three, it sort of is not constrained by Moore's law or something like that. And since there's a flexible architecture, you can maybe resolve like certain issues on building better fundamental computers. Pursues label fields and standards of its growth rate, distribution, or research by source type. Top 12 most prolific nations. Okay. Yeah, so there's been a lot of growth. Distribution. Showed up in journals, papers, books, book series, books, trade journals, other shonen. Yeah, so it's mostly papers at the moment, which is very fitting of a growing field that still remains not super accessible, at least in terms of the compute itself. Okay, what are the top 12 countries? Okay, the US, China, Germany, UK, India, Japan, Canada, Italy, France, Australia, Russia, and Spain. Sensible. Okay, yeah, the US is leading this by far. It's probably equal to like China plus Germany plus UK plus India. Yeah, pretty much. Distribution by subject area. Okay, so physics and astronomy, computer science, engineering, math, material science, chemistry. Yeah, so you would expect physics to be more of dealing with the fundamentals. Computer science maybe deals with like algorithmic stuff like cryptography or quantum information. Engineering probably deals with like building. Math deals with like theoretical stuff. Material science maybe deals with like building quantum computers, and the rest are like applications. Top 20 global affiliations. Okay. So CNRS leads that. Um, but oh, CSA leads this. Okay. But that's like the entire output of a country. And then CNRS is similar. UO is Oxford, MIT, Waterloo, Berkeley. Uh, USTC is, I think, 中科大, right? I think so. UT Tokyo, Caltech, NIST, Tsinghua, Maryland, Harvard. Yeah, so it's definitely the perceived schools that are strong in computer science are leading the field. Okay, quantum computing systems. All right, now we're getting to the meat and potatoes here. Yeah, okay. Yeah, so oh shoot. Keep mispressing. I don't want to use this. Not interested. Yeah, so a single qubit is represented by like a state like phi, where alpha and beta are parameters from between 0 to 1, such that alpha squared plus beta squared is equal to 1. And then it's entanglement of the 0 state and the 1 state, so that it's not like 1 alone, but the squared parameters for alpha and beta represent the probabilities, which is why this is like a probabilistic distribution. Yeah, so orthonormal basis, you can treat it that way. Um, and then you can use the block sphere to represent it using like this azimuthal angle and this radial angle. Felix Bloch. Yeah, and then you can use Dirac notation. Um, it is miles more compact than the equivalent matrix representation. Very true. Yeah, bras and kets. So vectors are communicated via kets. Hence the vector A, which stated as A, and bras used to experience dual vectors. Uh, yep. Okay. Uh, every prospect will lead to a complex entry with the limit that all the squared absolute values sum up to 1. Yeah, it is essential to bring up that these inseparable complex numbers turn to be among the two potential levels dependent totally of their chances to happen. And so, like, you can say that you can have a probability distribution function. Um, yeah, so Dirac makes it easier. And then you could like also write it with like some better notation. If you want to like deal with like states with more zeros and more ones. But yeah, in terms of like notation, it shouldn't be that hard. Oh, the tensor product. Okay, Kronecker product. PQXY, PXQY, log matrix. So I'm taking the multiple quantum state, applying a quantum gate to a quantum system. Yeah, since all quantum gates can be represented as unitary matrices. Tensor product. Okay, yeah, that makes sense. Y is 0 times 0, 0, 0. Well, if you have, like, say, 1, 0, 1, 0, so then it's 1 by 4. So then you have 1, 1, 0. So 1, 0, and then 0, 1, 0. So yeah, 0, 1. Again, it's 1 by 4. 1, 0, 1, 0, 0. Yep, okay. Yeah, this is the worked through idea. Yep. Superposition and entanglement. The capacity of a quantum system to be various states simultaneously. Yeah, here and there, up and down, close and open. Input and process. Experimental introduction of superposition of unknown photonic quantum states is furnished. So solid indeed that is reversibility and computations was raised. Yeah, so reversible computation refers to the idea that the input state can be recovered from the output state. Physical and logical. Quantum computers are reversible. But quantum computers cannot be copied. Yeah, it's because you can always construct like an inverse matrix. Okay. Yeah, this is a single qubit quantum gate. So rotation. And so sigma is the sum of a bunch of commuters. Bloch's theorem for any single qubit U. You can decompose that. Yeah, this is sensible. Just like a rotation matrix in general. Two XOR gates, therefore pair. Perfect control gates, using quantum error correction coding. Yeah, quantum error correction is the rising field right now in quantum computing. Okay, and then we go into the architecture. Yeah, okay, I think I'll have to save this for tomorrow since this seems like a continual section that analyzes the different technologies. And so the basics are kind of straightforward, but you also like it's a very brief overview. Yeah. So if you really want to gain fundamental understanding, read Nielsen and Chung. Yeah. Yeah, read this textbook. Um, I just started recently and it's been very good, but gotta keep pushing. Hopefully I'll finish it by the end of February.